Assalamu alaikum, ladies and gentlemen. Welcome back to another live stream. Let me share the stream. Okay, let's go. Come on. Okay, great. Let's share. Please make sure to join my Discord server if you want to get notified. Okay, oopsies. Hey. Let's go. Okay, this is gonna be an interesting adventure today. So let's pop out the chat and let's go into VS Code already. Okay, let's go, man. So let's create a new project. So cargo new, I don't know, I'm gonna call it, I guess, Codotaku scripting language. Codotaku scripting language. Alright, cargo new, Codotaku scripting language. Let's go. So Codotaku scripting language, we're gonna go inside of that. And so we don't need this anymore. Let's go. src main.rs. Zoom in. Let's open up the terminal and let's add Chomsky. So we're gonna be using this crate, though I'm not gonna add the stable version. I'm gonna use the latest version because Chomsky is going through a lot of changes now. So I'm gonna use the GitHub version directly. So yeah. Let's go. Just gonna copy the link right here. Gonna come here, cargo add, --get, Control-Shift-V, and there you go, done. I'm using unstable Rust, by the way, so we could also add, nightly Rust, so I guess we could also add unstable. Not sure if that really matters in our case, but anyways. So that's basically it, I guess. Now let's compile this up. So we're using the main branch of Chomsky, which is the alpha version of the version 1.0.0 or .0. Anyways, so we got hello world, great. So let's start our parser. Oopsies. So where's my chat? Okay, there you go. Let's go. All right. So let's get started. Okay, cool. So first of all, we're gonna have a file here which is gonna contain our sample.cdtk script, I guess. And for now, let's start by parsing some numbers. So we're gonna start very simple and, you know, keep on going to the next level, step by step, basically. Okay, so let's put some number there and let's try to parse it, I guess. So first of all, we need to load the file, of course. So let expression, well, we should call it a source, maybe, fine. And let's say cdfs read to string. There you go, read to string. The path in our case is sample.cdtk, since it's in the root of the project. Okay, great. So that gives us the result string error. Let's just unwrap it. And for now, and yeah, we got the source string, great. Now let's actually create a parser, a Chomsky parser. So of course we're gonna be using parser combinators in Rust. It's similar to iterators in that it is lazy and it's highly composable. But anyways, I think the best that I can do is just to show you how it works, I guess. So let's go fn parser. Okay, so this would return an impl parser. So yeah, let's first of all actually use Chomsky Chomsky prelude, yeah. Prelude. We're just gonna import everything in the prelude. It would contain most things that we're gonna need. Not everything, but most, I guess. Okay, so what's up with the autocomplete now? Let's see, impl parser. I'm not sure why it's not autocompleting it. But yeah, basically we have a trait called parser in Chomsky right now. Oh, let me try maybe to restart the server here. It's kind of weird. Let's start the Rust analyzer because it seems to be broken right now. Maybe it doesn't play well with cargo crates from Git, but yeah. Traits implemented. Okay, so right now we're getting some autocomplete. Great. Okay, so first of all we're missing some lifetime specifier. The previous version of Chomsky needed a lot of allocations, so they actually changed that, or they're currently changing that, right? For the newer release of 1.0. So we're gonna need the lifetime of the source code, right? So this is gonna be the lifetime of the source code string. So src. So we don't have to basically allocate a string every time. Like if it's already the string already exists in the input string, then we don't have to allocate a new one, you know. That just wasted allocations. So anyways, so we have I, which is input. It could be all sorts of stuff, but we're gonna go with the input. Let's go with src stir. So it's gonna be the source code or the input of this parser would be just a string of lifetime that have a lifetime src, right? So what is next? The output. Okay. So for the output, let's go with okay, let's start simple by going with, I guess, U32 maybe. And yeah, I think that's basically it for that. So we're saying impl parser, we're using basically the trait to tell the compiler to just figure it out yourself. This is not a dynamic dispatch. This is actually being done at compile time. The compiler figure out what's the real type, you know. Here we can just say something that implements this trait, right? At compile time. Okay, cool. So let's see what we could do now. So we're basically gonna print line. So this is how you use the parser. So comma parser, you call it, right, to basically construct the parser. Kind of like an iterator. When you construct it, you don't consume it, you know, directly. So like when you construct it, nothing really happens. You just get a new iterator. This is the same with parsers. Anyways, so let's actually use it right now to parse the source code. Okay, so if you need, for example, let's say some allocations while you're constructing the parser, then those aren't included when you actually parse something, you know. It's just when you actually create the parser. So you can actually store the parser in a variable and reuse it for multiple expressions. But for now, let's keep it simple like this. Expected, so this is a string. Let's actually say as sir. Okay, and now parsers on. Yeah, let's make this debug. And there you go. Let's go. The trait bound Chomsky. So now let's just start with basically too simply parsing integer. So how are we going to do this? Well, there's already a built-in parser in Chomsky for this. It's called integer, and you give it the radix. Is it like radix of 10, basically decimal numbers, or 16 hex, or 8? Is it 7 or 8? I think 8. Yeah, 8 octal numbers, etc. But yeah, so we're just gonna go decimal numbers dot 10, basically 10, right? And then we need to do something about this, what we want to do with this. Okay, cool. So I'm gonna turn it into a slice, I think, and then I'm gonna convert it from a string. So basically this to slice, make sure that it's like, it basically converts the output of this parser into a slice of the input based on the current parser's span. Now the span, it could be used here, so we don't have to allocate a new string here, first of all, and second of all, it's also used for error handling. But yeah, okay, so from stir, so we can convert it to a U32. So the compiler would actually infer what type we want to convert to, but you can't do it explicitly like this. But we don't need that, I think. And then, of course, parsing could fail. So as we know that this would never fail because we're parsing only an integer. So we could just say in wrap, and we're pretty sure that this would never fail anyways. And there you go, we have constructed our first parser. It just parses an integer. That's pretty much it. Okay, so cargo R, let's see what we got. Okay, so we got a parse result with an output sum 1000 with errors, no errors. Okay, great. All right, let's go to the next step, I think. So the next step is, let's say we want to parse some floats. If we actually run this, well, this is what we get. Hold on, let me zoom in here a bit. So we get a parse result, output none, and errors. We got one error, which is an empty error. So this is not a very useful error because this is by default in the newer Chomsky. By default is empty error for the fastest parsing possible with no overhead when it comes to error handling. But as you can see, it doesn't really tell you anything about what happened, what goes wrong. It only tells you that something gone wrong, but how, where, when, who, etc. It doesn't say anything about that. So to actually change that, we could go with extra. This is a namespace, of course, in Chomsky, and then we can go with error, all right? And then here the E, the error type. So the error type, there's multiple error types depending on how much overhead you want. Like, it's basically a trade-off between overhead and what is it else? Yeah, performance and how helpful is the error, I guess. But we're just gonna go with simple error for now, right? I think that's more than enough for now. There is also rich error, there is cheap error. So let's actually go with cheap first, maybe. Show you that first. The S, do I really need the S? It doesn't say an error though, so let's try this out. Okay, so this is the cheap error. So by default, by the way, this is actually empty error by default. Because if you see here, I'm not sure if it's, well, never mind. I need to look into the documentation, but never mind. Anyways, so this is by default what it is. It's just set to this. So it does give you only empty error. But now let's actually, if we use cheap, this is what we get. We just get the span of where the error happened. In this case, it says from index 4 to index 5, right? So this is 0, 1, 2, 3, 4, right? 4. So this is where the error happened. This is the span where the error happened. But we could go even more fancier with a simple error instead of cheap error. But this one, as you can see, it does need a lifetime of the source code because it would basically reference it, right? So we gotta pass it that. Struct. It also takes one generic, which is the input, I think. We're gonna go with char, and let's go cargo R, and there you go. Now, instead of just a span for the error, we actually get found dot at 4 dot 5. Notice that it actually referenced the string portion where the error actually happens. So basically our parser doesn't recognize what is this because currently we're only parsing integers. So let's actually do that now. Okay, so how are we gonna do this? Well, let's go back to our integer parser. And first of all, what we want to do is to basically ignore a dot, right? So we're gonna say then ignore just a dot. So as you notice here, this is functional and declarative. So you basically tell it exactly how your parser works instead of a whole state machine of if conditions and, you know, imperative flow. So that really becomes very messy real quick. I mean, parser combinators aren't as easy too. They have their own downsides, but at least for me, I prefer them. They're much more readable. But yeah. Then ignore just a dot, and afterwards, then we're gonna parse another integer. This time though, instead of int, I'm gonna use digits, radix 10. Why that's the case? I mean, digits and integer they're both built-in parsers in Chomsky, though they're kind of the same but different in one thing. Like integer is more constrained than digits. So while integer wouldn't accept something that starts, I guess, with 0, which is, so let me see, parser that accepts a non-negative integer. So there you go, an integer is defined as non-empty sequence of ASCII digits where, so this is the difference, where the first digit is non-zero or the sequence has length 1, okay? So the first digit shouldn't be 0, otherwise it won't be accepted. So something like this wouldn't be accepted for integers. But in floats, you do want to be able to do something like this. That's why we're going to use digits instead of integer. Okay, great. So, all right, what we got now. So then ignore just a dot, then get some digits. And yeah, now I guess let's maybe can we do 2 slice here? Okay, and then can we say from stir and in wrapped? So basically we can parse it to a float, and so a float, let's make this f64 I guess, and then we unwrap if there is any parsing error, which should probably be none because the parser wouldn't allow that in the first place. So let's see what we got. And yeah, we got it. So right now we're actually parsing floats. So 1000.256. Great. Now one problem though with this right now is that if you have some spaces, you know, in the end or the start or both, it's not going to work out because it's going to tell you that it's found a space at 0 to 1 here, right? Which is not great. So how we can actually fix this? Simply by saying .padded, pretty much. Now if we run this, there you go. So right now it would actually ignore padding spaces, right? It doesn't matter. That's great. Okay, so what's next? What's next? So this is our float parser, or should I say number parser. Now we do want to also be able to parse some symbols, basically when you reference a variable. So like you say x plus y or whatever, but basically this variable right here, you want to be able to parse it. So we want to parse an identifier. Let's forget about the number for a second, and let's just go ahead and go with, so we're gonna return a string and src lifetime, same lifetime as the input of course. So here we're gonna actually say text identifier. Again, we do have a built-in parser in Chomsky for identifiers. So parser that accepts an identifier, the output type of this parser is char stir. When C is char, so basically it can work with char, U8, whatever, you name it. An identifier is defined as per default identifiers in Unicode standard Annex 31. Okay, cool. So let's try this out actually, but of course let's add the padded maybe. Actually, we don't need that right now. So let's cargo R. Good. Hello. And there you go, some hello. So we're getting the identifier. Now, yeah, we have figured out how to actually parse an identifier, right? And we have figured out how to parse a number that is floating number, right? Now, you're gonna notice something interesting. This is one of the downsides of parser combinators, which is its explosion of types, because this is all done at compile time, like the combination stuff, for best performance, for best runtime performance. But of course that do hurt the compile times. But either way, that's not our business right now. What's the problem right now, to me at least, is readability. So I'm seeing all these inlay hints, which becomes very messy. So here's a little feature that I found myself. Which is, if you go to inlay hints, right, instead of on, you can say off unless pressed, right? So instead of off, you just say off unless pressed. And then the inlay hints are hidden by default and show when holding Control plus Alt. Okay, so now if I do Control Alt, look, I can see the types. Without Control Alt, I don't see them. So that's a neat feature for such a problem. Yeah. So now we got the identifier and we got the number. Now how we can tell our parser that we want either to parse a number or an identifier. So there's two ways of going. Actually, there's a lot of ways to go about this, but there's two main ways, you know. So number or identifier. Of course, the order matters. So the trait bound from stir. Okay, gotcha. Now the first problem that we're gonna find here is that we have some types problem, right? Why that is the case? Because identifier is a string, right? And number is actually a number. Too simply, we're actually parsing it into a number using from stir. So right now we actually need a struct called, let's say, expression, right? And this expression would hold, actually, should we go with, yeah, we should go with enum actually, sorry. Let's go with enum expression. Is the live stream fine, by the way? Let me make sure that is the case. Great, I mean, seems to be streaming fine, I guess. Let me just make sure. Okay, seems good to me. So yeah, let's continue. Let's continue. Did I actually post it? Okay, cool. All right, so let's go. Let's get going. So we have enum expression. It would be either, let's say, identifier or number, right? So either a number, it's going to be f64, or an identifier. So this is a tagged enum, and the identifier though would be a stir. But of course, Rust would complain about missing lifetime specifiers because it needs to know how much this string would live, as long as what. So we can actually declare a lifetime of the source string, of the source string that we're parsing, right? And then we're basically going to tell Rust that this identifier string would actually live as long as the source string, or at least, you know, maximally as long, I guess. But anyways, so now what we could actually do after this is, let's just remove this. Well, I mean, let's keep it fine. I'm gonna show you why we're gonna remove it later, but anyways, so map, and now we can do map, and then here closure, and sorry, number, I guess. Control Alt. Interesting. So it says, you know, reference of unknown. So, oh, really? Oh yeah, my bad. It should be before the padded. Otherwise, it would also include the spaces, I guess. No? Yeah, it's kind of confused right now with the types everywhere. So, but basically, there should be an f64 at this point. There you go. So, what we need to do with this number, we need to actually make an expression. So expression number. So we can actually merge these together using an OR, since they're gonna have the same type of expression, just different variants of the expression, right? So okay, great. Now instead of doing it this way, we can also just directly say expression number instead of creating a new closure for no reason. There you go. And now the identifier. So here we're also going to map this. We're going to map it to expression identifier, right? And same thing with that one. There you go. And now, what's up? Is it the problem? Padded is the problem? Number to be an enum that returns third but returns expression. Oh yeah, my bad. We're gonna need to basically change this. The other problem with parser combinators is the fact that errors become quite weird and long depending on how long it is. There is some fixes though for that, and in fact the Rust compiler itself is actually working on that, so it's also more of a compiler problem than the actual technique itself. But anyways, whatever. So like you could box these expressions, these parser nodes, to make the compile times better, and you're only gonna get the hit of allocating the box while you're actually creating the parser, not while you're parsing, so it's pretty much free when it comes to actually parsing the string itself. But anyways, so instead of source string, we're gonna, well, not here, this is the output, right? So we're gonna change it. Instead of that, we're gonna go with expression, and we're gonna pass it the lifetime of the source string. There you go. Cool. So now expression doesn't implement debug. Let's actually implement debug so we can use the debug printer. So drive debug. There you go. Now let's run this. Okay, parse result, output some identifier hello. Look at that, cool. And now what if I change this now to a number instead? And there you go. We can parse numbers too. Great. So we can either parse a number or identifier right now. Great, that's a good start. So yeah, I mean, I could have, by the way, inlined these into one expression. So like it could be just like this. I could have just returned this. Oh, sorry. Maybe something like, yeah, something like. But first of all, this padded right here, instead of putting padded here. Now the problem with this is that padded would only affect the number parser here. But for the identifier, we're gonna have a trouble there. There you go, found H at 1, 2. So yeah, that's bad, right? So what you gotta do, you also gotta add padded here to make it work. And there you go, identifier hello. So now it works. But instead of doing it twice, you could just remove it from both. No need. And then do it afterwards here, dot padded. So after, merging the two parsers together, number or identifier, then you can say padded, and then it would basically affect both because they're pretty much the same parser, kinda. They have merged into the same parser. But anyways, some identifier hello, great. Okay, so that's pretty nice. Yeah. So as I said, we could have just too simply, just inlined this. So you say number here. And identifier, you could have done it like this, so you don't need any of this right now. But as you can notice, this is quite messy, so that's why we basically put each little parser. So we create parser from subparsers to keep things very understandable, I guess, and readable. So yeah, it's kind of like abstraction basically. I mean, it is abstraction after all. Anyways, let's go back to what we had. Great. Okay, so let's go to the next step right now. Let's say we want to parse a let expression, something like let hello, I guess, equal to I don't know, to a number, right? Or identifier or whichever, right? So let hello equal to, just like Rust, to some degree. So how we can do this? Of course, there's also going to be a semicolon here. Okay, so how we can do this? Well, let's see. All right, so let, but of course we cannot use let because it's already a keyword, but we can actually do it like this, and it would work just fine. So let is equal to okay, let's see what we got. Okay, so the first thing would be text keyword. This is another built-in parser. So why I'm saying built-in parser? Because there's parsers like these that you can make yourself, but there's also primitive parsers like this just right here. These are primitive parsers. You can also make your own primitive parsers, but I haven't honestly checked that out. And you shouldn't need that really. And even if you need it, you probably want to actually contribute it to the library directly anyways, so they can make it into a primitive. But these should be more than enough to get you started, I guess. But anyways, so we got text keyword. So the keyword in our case here is let. And then, well, first of all, we want to ignore any spaces after it, right? So we're gonna say padded, and then we want to parse equals, and we don't care about equals, we just want to parse it, right? So we can ignore it, right? Then ignore just equal. Yeah, this could be a little bit challenging. I actually still trying to learn this, the way of thinking about this. I kind of get familiar with it a bit, but it was pretty hard for me to grasp at first, especially without any in-depth tutorials out there. There is the official tutorial, though it's a bit outdated right now for the alpha version. But yeah, there's also the examples. These are basically the resources that I kind of start to understand how it works. But anyways, so then ignore just equals, and just equals we're gonna pad it, so we're gonna ignore any spaces between them. And finally after that, well, is it really finally? Yeah. And this gotta be an atom, let's say. I don't know what to call it. I mean, we can maybe call it expression. Not really. Or maybe we could call it value. Yeah, why not, I guess. So number or identifier dot padded, that's the value. So now, so after the equal, we're expecting a value. Then we're gonna capture a value. Okay, great. So basically, first of all, we parse the keyword let, right? Though we should ignore the let keyword. We just want to parse it, but we don't care about it. Then ignore. And you may say, why would we do it in the first place if we're just going to ignore it? But the thing is, we're ignoring just the output of it, but we're not ignoring its actual parsing process. So like the thing is, what happens is that we go through a parser until it fails. If it fails, like for example, let's say we here number or identifier, we start parsing the number. If the number parser have failed, then the identifier parser can get to run, and if the identifier, you know, successfully parsed its thing, then it would return its output, you know. So that's basically it. If number have successfully done its thing, then identifier wouldn't run. So that's how it goes. It's pretty much lazy. You only pay for what you get. Anyways, text keyword let, then, well, ignore then. Ignore then. So we want to ignore the previous output. Ignore. But the problem with this, ignore then. So we have this padded here, which is kind of I mean, I think we can remove it, right? And hold on, ignore. Can we just say ignore? Ignored, yeah, I guess. Ignored. Well, dot padded ignored. Right? Ignore the output of this parser. Okay, cool. Dot padded ignored. Let's see. You have a compile error. Yeah, my bad. So we gotta return something, of course. Our parser right now, let's return let expression. I guess. What's up? Then value. So let's padded ignored, then ignore just equal dot padded, then the value. But of course, yeah, we gotta map this to an expression. And here we're basically gonna get two things, I think. Hold on. Actually, we're not parsing the name though. My bad. We're not parsing the name of the variable. So how are we gonna do that? Padded. Ah, I see. So we can say ignore then text identifier. Okay, so that was what confused me there. I was expecting that, but anyways, so padded ignore then, so we're gonna ignore let, then we're gonna parse this an identifier, then we're gonna ignore this equal but take the output of this one. Notice that this is ignore then and this is then ignore. So ignore then would actually parse one thing, so it would basically ignore the before, the parser that comes before it, or the output of the parser that comes before it, but take the second one. Then ignore would actually take the output of the first parser, the parser before it, but take the output of the second parser. So this no, I mean it would ignore this one, right? So anyways, let's map this right now. So we have two things that we captured other than the ones that we ignored. We have two things. We have the identifier and we have the value. So identifier and the value. If I do Control Alt here, notice the identifier is a string and value is an expression. Cool. Now we still haven't made a branch for the let branch, right? For the let variant, sorry. Okay, so how are we gonna do this? Well, we need first of all the identifier, like basically the name of the variable. So it's gonna be a str and src lifetime, and we're gonna have, so here notice that we're not allocating anything, we're just using, you know, a span of the input string, right? So we're just referencing the input string. Anyways, so the second thing gonna be, what is it called again? Yeah, well, it's gonna be the expression. Now here is something interesting here. We're gonna get recursive type expression has infinite size because you cannot really figure out what is the size of this, you know, because like you have expression of expression of expression, so where are you gonna end? This doesn't have a, this have basically an infinite size, right? So how we can break the loop, break the recursion? Well, we could use a box. We could allocate this in the heap, and so we're only gonna store a pointer to this expression instead of the expression itself. And so we break the recursion, and now we can actually do this. So it doesn't need to be a box, it could be an RC or whatever, but I think box is fine here. So let's go. So identifier and value. Okay. And what we're gonna return is expression let, and then the identifier is the first one, and the second one I'm gonna create a new box, or we could just say value.into, and it would basically make a box out of it. All right, great. So yeah, the annoying warnings, let's do this. So allow what? Hold on a second. I'm just making sure that the chat isn't broken or something, because it's quiet today. Okay, it doesn't seem to be broken. Okay. All right, so let's allow did code. Oh, well, yeah, allow did code and in used, and warn. In used must use. Well, not warn, actually forbid. I don't even know why this is not a default, but anyways. Okay, let's go. Let's go. So now watch. Text keyword let. So I think we should be good to go now. Cargo R. And output none found a semicolon. Oh yeah, we're not parsing the semicolon just yet. We're gonna get to that. There you go. So we got some let expression with identifier hello, with the number 123.123. There you go. Cool. Now we need some way to actually, basically sequence the operations, like make a new statement. So we can make it so we parse a semicolon, and then we can make another let. This is let x. Let y is equal to 2.0, something like that, right? So we cannot actually do this right now. If we try to do this, it would say that it found the semicolon at 11:12, which is an error, right? So let's go ahead and do this. So how are we gonna do it? Well, before that, actually, let me show you something though, which is the fact that even beforehand, so this works, right? Yes, this works, right? But if we actually just made it integer instead, without a dot, without a fractional part, what's going to happen is it actually will fail, because it is expecting a dot here. It is expecting a dot there. So how we can actually fix this? So here, just dot. So we're then ignoring just dot, but we could say just dot or not. So that dot would become optional, isn't it? I think so, yeah, probably. Let's try this, I guess. Let's try this. Just dot or not. And then 2 slices from stir in wrapped. Okay, let's try this out, I guess. No. Interesting. Oh, my bad. I see what's up. So just dot, then text digits or not. Okay, so this also should be optional. So this should be here. Well, we don't want to ignore it though. Okay then, so we can just say then, right? And here we can say ignore, then do that, right? There you go. So then just dot, ignore, then text digits or not. This whole parser right here is optional. So this is basically the fractional part. I mean, we could put it into its own variable if we want to, just to make it clear. Fraction. So as you can see, fraction or not, because fraction is optional. And there you go. So it's cargo R right now. And there you go. We're getting a float 1.0, although we didn't add 0.0. Okay, so that's something we have fixed there. Great. All right, so what's next? Yeah, we wanted to actually do the let here. We want to be able to make, multiple lets. We want to be able to declare multiple variables. How we could do this? Okay. So then the value, after we get the value, we should try to parse, well, after I guess we map it. No, before that. We have to try to parse a semicolon. So how are we going to do this? Well, parse, sorry, not parse. We're going to say then ignore, maybe. Then ignore just semicolon. Okay, and what else? Then ignore just the semicolon. Okay, and then we're gonna try now here where the recursion happens. What we want here to do is, yeah, we want to ignore the semicolon, and right here we actually want to recurse. We want to get another, like, to reference the let here. Now if I try to do that, it wouldn't let me, because it cannot find that value, because we're still declaring this, right? So how can I fix this? Because this is like a recursive thing. where after the semicolon, this pattern will repeat again. It would recurse. So we can actually say recursive here. There's a parser called recursive, which would actually give you the let here, just like it's been declared already. And just wrap it in that closure. And what's up here? Let's remove this guy, I guess. Okay, there you go. So you have to return that thing. And yeah, I think that's basically it, maybe. Or let. So as you can see, then ignore, then our let. We're recursing here. Great. And then we're mapping. Now here we don't get just identifier and value. We actually here we get the identifier and an expression. Then this is gonna be probably something else, right? So let's go ahead, because we're basically also again capturing the let recursively. So this would be the identifier and the value, and we're gonna add another kind of tuple here, comma expression. Well, this is basically the next one, the next statement. So what should I call it? Let's call it then, right? What you're gonna do after that, right? So there you go, then expression. And of course we need to store it here, so we're gonna do the same thing as before, box expression src. So I'm just gonna copy and paste. There you go. Let's go. Now we're gonna say then dot into to box it, to box the expression, and there you go. Though sometimes it does have some stupid problem with that, so I guess let me do it explicitly. Yeah, sometimes that boxing with into doesn't work so well. It tells you that you need the type. I'm not sure why that's the case, so honestly let's just do it explicitly. Who cares, right? So identifier, we box the value and we box the then. Great, lovely. And there you go. So now we should be able to do it, I guess. The problem though that we're gonna have here is if we do this, I mean, let's see the good part first. So we have two lets right now. Let's see. Found end of input at 22:22. Huh. Yeah, that's not gonna work either way actually. Why? Because too simply when we reach the end of the semicolon, what happens is that there is no end then statement, right? So we just reach the end of the input instead of parsing something. So how we can fix this? Well, there's two ways. Well, actually there's a lot of ways to fix this, but what I'm thinking about right now, we could just add an end expression, I guess. And here, well, I mean, we could either do this or make this an option. I honestly think making it an end is better in this case. So anyways, so let's just go with expression let identifier box new then. So here, then ignore just that, then let. So instead of then let, we can actually say dot or not. So this would be optional right now. The recursion would be optional. Okay, so we break the recursion here. And now what we're gonna do, box new then. So basically, if then is a sum, because this is an option right now, we're gonna map it into a box. So we're gonna map it into the box new function, right? Otherwise, we're gonna give it expression end. Well, what I'm saying, no, actually no. We're not gonna map it because we want to box both. So we're just gonna say box new, then or expression end. Yeah, exactly. What's up? Expected option. Dot. Oh, sorry. Is it in wrap or? Hold on. What? So then is an option in wrap. Oh yeah, so basically in wrap, or my bad, and let's go. Now this should work out just fine. And there you go. We have some let x number 1. So let x equal to number 1, right? And then the then expression of the first let is the second let y is equal to number 2, and then finally the end, which is the then expression of the last one. And there you go. And we could just go ahead and say let z is equal to 3 and so on, and we'll just keep on going like that. There you go. So now I could actually parse declarations of variables. Great. You can also say something like this, you know. You can use identifiers. So as you can see, let x equal to a number 1, let y equal to identifier y. This doesn't make any sense, but there you go. We're not doing any kind of fancy error checking yet. Okay, great. So what's next? What's next? I'm trying to think of the easiest way to go about this. I mean, maybe we could work on the evaluation already. Maybe. Like, you can actually say something like this right now, I guess. No? No, probably not. Yeah. Yep, no. Okay, so how we could actually make this possible? Good question. So then let or not. What if we said then let or value? Yeah, I guess. I mean, both are expressions, so it should work, I guess. And there you go. So the end thing is identifier x. Hello, Bibin Lopez. Welcome to the live stream. I'm from Morocco. What about you? Welcome to the stream. Let's go. Alrighty. So we're actually good now. Should we go into operators right now? Operators is kind of a can of worms. Actually, let's start with unary operators maybe. It's not that easy to, but well. So basically we want to be able to, right now we cannot actually make negative numbers. And other than negative numbers, there's also the problem of having multiple negative signs. So if you have, minus minus, this would be a plus, So depending on how much negative signs and even plus signs, So you need to be able to parse something like this. It's kind of weird, but I mean, you have to. So how we can do this? Well, let's start simple and go on from there, I guess. Okay, so number, identifier, value. So I guess after the value, can have a unary operator. Maybe. Or maybe actually before it, yeah. I don't know. We'll see. Okay, so unary operator is equal to what? Good question. Just minus or just plus. So we want to accept both unary operators. And then we're gonna actually, hello Nami, no Dev, welcome to the live stream. How is it going? So we have just minus or just plus, right? And we're actually gonna convert the plus into a one float, right? F64. And the same thing with the minus. Just minus dot 2 1.0 f64. Sorry, minus 1.064. You'll see why in a second. So 2 is a bit similar to map, but while a map actually captures the inner value of the thing, of the parser, and you can, you know, in function of that, you can determine the output. The 2 function just, you know, converts that token, or sorry, that parser's output into some value, some constant value, regardless of whatever the previous value is. In this case, minus, we don't care what operator it is. We just convert it into minus, right? So just minus. Okay, cool. So what we're gonna do with this, and instead of, by the way, or, we could also use choice instead of or. So we could just add choice here, and then we can remove the or now, and just add a comma there, and there you go. Though we're gonna need a tuple here. This choice function accepts a tuple, not a variadic list. So type annotations needed. I don't think we're gonna need them later on when we're done. Okay, so choice just minus 2 minus 1 and just plus 2 1, and then, well, is it? I guess we're gonna need to fold, yeah. And there's 2 ways to fold this thing. Well, actually, first of all, it needs to be repeated, right? So we can have repeated plus and minuses. Like, it could be something like this, and we have to parse it. We have to be able to parse it. So how are we gonna do it? Well, we just say repeated. it's as simple as that. And this repeated would basically make it so it's either repeated 0 times or more times. If you did want it to have a minimum, you could also say at least or at most or exactly and stuff like that. So that's pretty cool. This is why I love iterators. And parsers are kind of like iterators. They're just super composable, super readable. I just love them pretty much. Anyways, so repeated. And then we could either collect them, you know, collect them into a vector, for example, or whatever. But we don't really need to allocate for this. We could just fold them into something, right? We can fold them into what's the result. Like, if you had something like, let's say this would result in a, so we're gonna basically fold from, we can either fold from the right to the left or from the left to the right using fold L or fold R, right? So unary operators are actually supposed to fold from the right to the left, and binary operators are supposed to fold from the left to the right. Right? Just like how you read an expression, a mathematical expression, you read it from left to right. But when it comes to unary stuff, unary operators, you actually should go from right to left. So in this case, if we add parentheses, it would be something like this. So it would be something like this, right? So we would do this first. So you would start from the number and then go on this, this, and this. This is the fold operation from the right to the left. Okay, good. Let's go ahead and do this. All right, so repeated, oopsies, sorry for that. Repeated dot fold. We said L or R. Right, yeah, we're gonna fold from right. And the first thing that we're gonna fold from is the number, or the value in this case. A value in our case is just an identifier or a number. So it could be either, like, for example, minus X or minus Y or minus 1, whatever. So here we're gonna say value, and here we're gonna have a closure. Let's go. Bruh, this is annoying. What's up now? It doesn't really tell me, I guess. I think it would be something like this. Good. It's expected to take 2 distinct Oh yeah, my bad. I see now. Alright, so A is going to be f64. So basically our operator, because we mapped them to f64 values, either -1 or 1 depending if it's minus or plus. And we're going to have the B, which is our expression that we're folding into. Great. So we could just say, I think we can just say A times B, is it? Cannot multiply f64 by expression, huh? Interesting. Well, I guess we gotta fold them into multiplication actually. Yeah, it would have been easy just to actually multiply them, you know, a parse time here, but we cannot do it because the value includes something that cannot necessarily be resolved at compile time, which is identifiers, or like variables basically. So instead we're going to turn them into a multiply expression, so we can resolve them at interpretation time when we actually interpret the expression. So let's make a mole variant of this, and it's going to be a box expression. So basically I'm just going to copy this 2 times, right? So this is the left hand side and this is the right hand side of the multiplication operation. Do I actually need that? Am I doing something wrong? I don't think. I guess we could just probably start from 1.0, no? Not sure. I mean, let's just try this. This is what I thought about right now. There's a lot of ways to solve the same thing. So expression multiply A with B. Huh? Yeah, there's gotta be a box. So that's the problem with this. We have to box each value. So more allocations. Mismatch types, expected expression, found f64. Oh, interesting. So A is f64. Yeah, it makes sense. Makes sense. So, we could actually make expression number. There you go, because it's expecting expression. And this should work, I think. So let's actually remove this right now. And let's just go simple, something like this. Now let's just make sure everything is working fine just before, like before. There you go. Nothing fancy. We have a let x equal to number 1.0 and then the end as the then expression. Good. If we do have minus though right now, here's what's going to happen. Oh, well, we're going to have an error. That's what's going to happen. Interesting. So found minus at 8,9. But what's the problem with it? Oh, maybe I didn't include it. Yeah, I see. My bad. So, yeah, instead of using here, where is it? Yeah, instead of using value here, we should probably use the unary operator instead because it includes the value. Yuppie, let's go. So then value, instead of that, we're going to go with the unary operator. Or the unary operator, I think. So basically everywhere we had value, we're just going to replace it with this one, I think. Okay, good. Good. So this is what we got. We got multiply number -10 times number 1.0, which is going to give us -1, right? If we had minus again, this is what's going to happen. We're going to have multiply -1 with the number itself, 1. If we also add a plus, again, we multiply -1 with -1 with 1. Can we actually fold these expressions themselves. That would be cool. Multiply number minus 1, because we can surely fold these alone. Well, what happens if we, well, let me just actually copy this. I'm gonna comment it out, and I'm just gonna experiment with something real quick. What if I said 1.0 here instead of value? Trait bound. Well, no, that's not actually gonna work. Right. But after that, can we actually do another fold? So, because these will be expressions. Can we actually do a fold again? But what would be the other? Weird. Anyways, this should be fine. We're gonna do it in the evaluation phase. Not the best, but it should work. Anyways, let's go. And yeah, we have done it for that. We have added unary operators. Right now, what we need to add is binary operators. So something like this, 1 plus 2. So how we can do this? Well, good question. Good question. We have to also account for precedence, by the way. Okay, interesting. I think we could probably go with binary operator afterwards here. And let's see how we're gonna do this. So we're expecting to parse a unary operator, right? And then maybe just plus, for example. So yeah, this is gonna be the sum, okay? So just plus, then just plus, and what else? Of course, this would be padded for spaces, I think. And what else? Unary operator, then just padded, and then the unary operator again, yeah. And finally, we're gonna map that to an expression. Okay, we're gonna get A and B, I guess. Oops. Probably it's a tuple. Yeah, it doesn't tell me. Interesting. Let's just say something like this, I guess. Doesn't tell me either. Interesting. Okay, so I'm supposed to know what this does. Cannot add expression. Oh, there you go. Okay, cool. So cannot add expression to expression char. There you go. Ah, I see. So we can ignore this operator thing. So, or actually what we could do, we could convert it into a function though. Yeah. We could do something similar to what we have done here for this one. Interesting. Just instead of replacing it with a number like this, we can replace it with a closure. Wild. Okay, let's see if we can do this, I guess. So this would be maybe I'm not sure what to call it yet, but let's see. So just plus dot padded. Though the thing is, we're gonna need to do this multiple times anyway, because plus and minus, yes, have the same precedence, but multiply and plus, for example, doesn't have the same precedence. So we gotta do it in another expression. Yeah. Yep. So basically the precedence is defined depending on the order of doing this stuff. So like the value have the best precedence here, right? Because it is included here. So the unary operator afterwards, and then there comes the sum and so on, I think. Anyways, 2, let's see how we can do this. I guess a comma b, a plus b. So if it's a plus, we're gonna convert it to that. Okay, let's just remove the padded for now to remove the noise. Okay, cool. And instead of doing this, yeah, what was it again? So it says expression to expression, comma, closure. Yes, okay. So this would be something like this, I guess. Oh, my bad. I guess no. Probably like this. Yeah, there you go. Cannot add closure to expression. So A is the closure. Yeah. Yeah, that's the first one that we actually capture. Makes sense. So we're gonna use that operation, right? So that's the operation basically. B is the unary operator expression, I think. But what is C? Don't know why it doesn't tell me the type. That's stupid. Then unary operator. Then what? Oh, actually the first one, the LHS, I think here. RHS then? What is it? So this would basically be operation. Expected. Yeah, this is probably wrong. This is probably should be like this, right? Yep. Cannot add to expression. The trait add is not implemented for expression. Huh? Yeah, my bad. So we gotta actually right now make them add. So we're just gonna copy this, paste, make an add variant, and let's make an add variant out of this. Though we could have maybe simplified this by implementing add, multiply, and stuff like that for the expression, and then it would do its job. Let's try it for this maybe. I don't know how easy that would be, to be honest. I don't know if it's worth it. Let's not overcomplicate things. Let's just do it the normal way. So instead of a plus b, gonna go with expression, multiply. Sorry, what the heck? Not multiply. Is it sum? What did I call it? Add, okay. So add the first expression a and the second expression b. And then now what? Argument to this function are incorrect. I think we need a box here, right? Hold on a second, what the? So a is a box expression and b is also a box. Argument to this function are correct. Expected struct box expression. Found the enum expression. Ah, I see. So we have to maybe do this then. Okay, there you go. Let's go. So we say operation LHS, basically left hand side with the right hand side. And that's for the plus. But now let's also do it for the minus. Dot or just minus. Well, basically I'm just gonna copy this one right here. That is before the or for the minus. Oh crap, what's going on here? Look at that crazy error. Okay, go. Hold on a second. What I'm doing. Hold on. Let's take this into a variable real quick, okay? Then x, right? Is so we can have some room here to work with. Okay, cool. So just plus to that. I guess let's have a choice here. And let's just take this guy here. And there you go. Now this would be a minus here. And this would be a subtraction operation. Subtraction. Okay. Where's subtraction? There you go. Okay. Let's make the subtraction instead. And now what? 2ab expression add. Okay, cool. Now the problem with this is that closures are by nature different types. So every time you create a new closure, you get a new type. So we gotta basically downcast this into a function, to a binary function. So as fn, I'm not sure if there's a better way though. Yeah. As if, and do I also need something like this maybe? Huh. What? Trait bound. Look at that error. Crap. It cannot be called due to unsatisfied trait bounds. Did I miss something? Okay, let's see. I think that should work. AB. So it would basically, yeah, let me actually make a little type here, type alias. So binary operator, right, is equal to fn, and it's basically gonna get a expression, I think, or is it? Yes, expression, and src here, and another expression, and it's gonna give another expression the same lifetime again. Of course, we're gonna need the lifetime to be declared, and there you go. Now can I actually say as binary operator, src, as binary operator, src. What about that? Huh. Non-primitive cast expression as fn. Oh, what the heck are you talking? Oh, no, not maybe in the right place. Yeah, it shouldn't be inside of the. Huh? Confused right now. What the heck I'm saying? Not here though. It should be in, well, basically this closure. Where is that closure? Yeah, okay. So let's actually make it into that. And now let's say as binary operator. Yeah, because we want to actually cast the closure, not the expression. Is that the error that I had? Maybe? Maybe. Yeah, I guess so. There you go. Okay, so I just Yeah, that's what I wanted actually. I wanted to cast the closure, not the expression that returned by the closure. Okay, great. So this should hopefully add for us plus and minus, I think, if I haven't missed anything. Great. Let's remove the spaces for now because we're not accounting for that just yet. Ah yes, we're not including this sum. So instead of unary operator, let's say sum. I should have probably let the let until the end. Okay, there you go. Okay, great. So as you can see, I got some let expression. The name of the let expression would be x. There you go. The value would be adding the number 1 with the number 2, right? And finally the end is the then expression. And there you go. Great. If we had minus 1 plus 2 minus 3 or whatever, oh, what should work? Oh, my bad. We're not repeating these, right? So we have just only parsed one pattern. So we need to actually repeat this operation. How we can do this? Let's see. Some interesting. Unary operator, then x, then unary operator. I think dot repeated probably. And then we can fold L instead of fold R. Right? We want to basically, like, mathematical expression should be evaluated from left to right if the precedence is the same. So which is it? This is the case, right? So fold L. The other in this case is the unary operator, I think. And then here we got a closure. It's going to contain, I believe, A and B maybe. I don't know what to do about this yet. What's up? Trait bound, fold R, unary operator. Let's see what we got. Trait bound, repeated. Oh my god. Okay. Fold L. Look at that type. Crap. Okay. Let me try to think here. So fold. Should this fold maybe be before the actual map function? Maybe. I mean, fold and repeat even. Maybe. Maybe not. No, so what's up then? That's weird. Oh. Could it be that it actually wants here the closure? Let me actually see an example here from the documentation. So where's fold L? Just plus ignore then int dot repeated. So this is the repeated pattern. A plus sum is equal to int clone fold L just plus. Yeah, my mind is going wild right now. I should probably stop here for now. My mind got stopped right now. But we got some progress going already. So map repeated. Map. But yeah, let's do some little parsing. Little basically let's evaluate this a bit, and maybe I'm gonna stop the stream for now, pause it until maybe tomorrow, and we can continue on this. So yeah, let's go. All right, so how are we gonna do this? Well, good question. So this would give us the AST, right? Right now we only can do something like this, basically. And we're not even handling parentheses just yet, though we're gonna do that hopefully in the next stream. So add number 1 and number 2. Great. Okay, so let's put this into an AST variable, and let's actually evaluate it. So this is our AST. I'm gonna unwrap it for now. And there you go, we got an expression. And we're basically gonna have an eval function, which is gonna take an expression, type expression. There you go. And it's basically gonna return some, well, expression again, pretty much, I think. Yeah. Mismatch types expected expression found. Oh, yeah. To do here. And other than expression, we also need a hash map where we can store the values of the variables. So for that, I don't know, let's call it maybe variables. Hash map. Okay, hash map. Should we actually use hash map? If we want to actually support shadowing, we shouldn't use hash map. We should use, let's say, a vector rotor, but let's just keep it simple for now. Let's go with hash map. And so the key would be probably stir, and the value would be expression, I think. Maybe not, probably. We'll see. So we do need the lifetime right now because we have more complex expression. SRC. So let's just sprinkle the lifetimes right now. Okay. Gonna need that here maybe too. Here too. And there you go. Okay, cool. So now let's actually match on the expression that we got. Let's control dot fill match arms, and there you go. So here we got gonna get our number, and yeah, I mean at this point we're just gonna return expression. I mean, we don't have strings yet, so I think we could probably just go with F64 right now. Yeah, I think. Or we could leave it like that, and in this case we reach the recursion end. We're just gonna return the number, right? Or isn't it? So mismatch types expected found F64. Okay. Not sure how I want to go about it yet, but we'll see. The identifier here. The identifier. So we need to basically get the value out of the variables, right? Cool. So identifier. And here we're gonna try to basically take it out from the variables. Dot get the identifier, if we don't find it, I think we're just gonna crash for now. Or we could make some sort of a null value, but I don't want to deal with that just yet, I guess. Match arms have incompatible types. Expected expression. Found expression. Huh? Expected. Oh, I see. I see. I guess we could just copy this. No? Cannot move. Ouch. I think we could probably... can we actually? I don't think so. Can you actually do this? No, of course not, because it contains a box, yeah. But we can clone it. Okay. In wrap and clone, so we can actually get at the value instead of a reference of the expression. Or can we actually just use the reference then instead of doing this? I think so. Well, not always. I mean, the input doesn't have to be, we can just go that way. The expression though, it could be either owned if it's new or borrowed. So we could probably go with a cow here. Yeah, maybe. Maybe we could go with a cow here. Gotta import that. And what's up now? Okay. And now here, what we got? Mismatch type is expected if 64. Found if 64. Huh. Oh, I see. Can we actually do this? Oh, there you go. What? Well, can't we just say this? Why not? Oh, because we gotta make it into a cow then. Can I say into? No, I can't. Okay, so let's say that this is well, owned. Although we should be able though to just return the expression itself, to be honest, but yeah. Anyways, so cow owned, this is found to be of type. But I think that's fine, right? What's up? Weird. Anyways, so expression identifier, variables get identifier. In wrap clone, match arms having compatible types, expected cow found enum expression. Now here we're gonna actually have a new owned cow again. I mean, are we gonna have an like a borrowed expression anytime anyways? Good question. Honestly, I think I'm pretty much probably complicating it. Let's just clone these things for now. Later on we can worry about optimization. Yeah, pretty much. My bad. Let's go. Okay, so now here the let function. Sorry, the let expression. So here we're gonna have the name, right? We're gonna have the, what is it called? The value and the then branch. Right, good. So we're gonna say variables. Insert, right? Yeah, I think so. The name is that and the value is that. And then we're gonna actually return the then. So like we're gonna have something like this. And maybe we can say in wrap here. And then we could actually return then, well, eval then. Eval then variables. Well, are we actually wanting to own the hash map? I don't think so. Mismatch types. Consider inboxing the val. Sure. Eval then. Oh, it's boxed, yeah. So can I, yeah, inbox it. There you go. Cannot borrow variables as immutable. Is behind. Oh, my bad. Let's make this mutable reference. And let's go. Now the multiply. So we're gonna have left hand side, right hand side. Same thing with the other ones. Oops. Well, we could just copy the whole thing, yeah. Okay, cool. So how we're gonna do this? Well. Good question. Match. I think we can match on the left hand side or right hand side like this. And depending on the combination, we're gonna do something. Oh crap. What the heck? No. No way. We're gonna not worry about the other cases. Mismatch types expected expression. Let's just say unreachable for now. Please, thank you. And let's just handle expression number. Number with a number. Is it like this? Huh. I guess we should have this, right? Yes, okay, cool. So we're gonna have number one, or basically, yeah, pretty much LHS and RHS here. And here we could just like, I guess, times RHS. Is that the case? Mismatch types expected. Found the enum expression. Huh. What? Try wrapping. Oh yeah, my god. Expression number. Mismatch types expected struct. Found the enum expression. Eval returns an expression. Just get returns an expression. Okay. What else? Okay. Match. Oh, these are boxed. I see. Can I actually just inbox them? There you go. Cool. And there you go. So if they are numbers, we're just gonna multiply them together. But well, if they're numbers, yeah, we're gonna have multiple cases here. But yeah. What I'm gonna do about the other ones? So there could be a number. Well, what about just saying, yeah, actually I could just evaluate them, my bad. I don't know why I'm overcomplicating this. Yeah, just evaluate them. Gotcha. LH, but no, what the heck? Expression number. I mean, if anything else, actually. Then we're just gonna say expression But does that make any sense though? Eval A with mutable variables and eval B with mutable variables. Arguments, so does any variant are incorrect expected struct box. Huh? Okay. Ah, yeah, I see. Okay, see, box, yeah. I should probably just define, honestly, the operations on the expression. And anyway, cannot mutate immutable variables? Huh? Oh, this actually needs to go directly to the eval function. Yeah, I think this is not the best way, I guess, to go about stuff, but let's just actually try this just with multiplication and stuff. Let's forget about the other ones for now. For the end, I mean, if we reach the end, what are we gonna return? I mean, I guess nothing. Yeah, pretty much expression end, I guess. I have no clue what to do with that. Expression add and expression sub. Okay, so let's keep these for now, for later. Oh, actually right now I'm only handling some. Interesting. Okay. So let's actually turn this into add instead. Add. Good. Let's put it right around here. Let's make this small as a to do. Right, so let's try this. Let's try this. I have no clue what to expect. Front line, AST debug. Huh? Are we handling the let? We are. So so why is it giving me the let then? Interesting. Eval then variables. Huh. Okay. Yeah, I think my brain has stopped right now. Okay. That is unexpected. Yeah, we can continue tomorrow pretty much. I think my brain is shutting down right now. It's 2 o'clock, 2 a.m. So yeah, that was it for this stream. Though we have done a lot, like parsing wise. So that was a lot of fun. So yeah, that was it for this stream, and see you in the next one. Goodbye, everyone.